Well, dear students, see, this is kinetic theory of gases. This is the most important theory, and we can say that this is great milestone of science. Why this is called great milestone of science? In the chapter one, in stoichiometry as well as in atomic structure, we have developed the models for atomic models for matter. So success of this theory basically provides a strong evidence for this atomic theory of matter, right? So that's why this theory is called a great milestone of science, right? So this theory, proposed by this three scientists, Clausius, Maxwell, and Boltzmann, right? And see what we are going to study in this theory. After this theory, after the formulation of this theory, and after the postulates of this theory, see, we are going to study here for how gases exert pressure and what is the formula of the pressure of gas, and what is the formula of energy of gas molecules, and different kinds of speeds, and try to understand the difference between speed and velocity for gas molecules. So these are the main points of this theory and discussion of this lecture, basically, right? So see, this theory is based on certain assumptions, and you know, the first assumption is kinetic theory of gases is first assumption for this theory is that gas molecules are always in random and ceaseless motion, right? Gas molecules, gas molecules are always in random and ceaseless motion. Ceaseless motion. So see, these are two very important words: ceaseless and random. Means there is no preferred direction for the motion of gas molecule, and ceaseless means there is no force of attraction between the gas molecules, right? And second point, is the gas molecule are separated by the gas molecules are separated by the distance that are large distance that are large large compared with their size, compared with their size, right? Means we can say that the volume of a single gas molecule is negligible compared to the volume of container. Actually, this point of kinetic theory of gases is simplified in this way also. What? The volume of a gas molecule is negligible compared to the total volume of container. Means what I am trying to say, that the gas molecules are identical and they are very very small, right? So this is the meaning of this point. And now the third point is the gas molecules are in the different moves in the different direction. So that I have covered in the first point, that always they are in the random motion. So in this point, the molecules exert no force on one another between the collision, means ceaseless motion. Their motion is ceaseless, right? So one important point, the molecules, we can summarize this: the gas molecules, right, exert no force, exert no force, no force on one another, one another, right, between collision, right, between collisions, right, and and move in a straight line, move in a straight line, straight line between collision, between collisions, right? So basically, they exert no pressure, no force of attraction on one another. That's why I have used here this ceaseless word, right? And collision of molecules with the wall of the container is elastic. This is also very important point. The collision of gas molecules with the wall, with the wall of the container, wall of the container are elastic. Elastic. This is important point. Elastic means no energy is lost during the collision. Elastic, that is no energy, no loss of energy, energy during collision, right? So these are the main and important feature of this kinetic theory of gases. On the basis of these assumptions, we can derive the formula for pressure of the gas, and we can link that formula with the equation of state, which summarizes the properties of gases at a relatively low pressure, right? So with this, we can try to find and derive the formula for pressure of a gas, right? After that, we will try to justify the Boyle's law, the Charles law, the equation of state by that formula of pressure, right? That is based on this assumptions, right? So first I am trying to derive the formula for pressure, right? So first I am taking here formula for pressure. Formula for pressure, right? Okay. Now for this, we can first we should know that how these gas molecules are moving, which type of motion is there for gas molecule. So you should know that the gas molecule like spherical we are considering here, and this motion of this motion of this gas molecules, right? So if these are the gas molecules, so their motion is 3D motion. Motion is 3D, right? So means simultaneously they have x component, y component, and z component of their properties like velocity. If you consider velocity, then they have all three components of velocity, right? So if you consider a gas molecule like this, and suppose that this is moving in this direction, right? So v so all three vectors are present simultaneously here, right? Okay, so suppose that this is vz component, this is vy component, and this is vx component, right? So this is a gas molecule, and this has the velocity. So all of you are knowing velocity, and it is a vector quantity. So is it feasible for us to express the velocity of gas molecule? The answer is no. If at any moment of time, if question is asked, what is the velocity of gas molecule? So if you have taken only one gas molecule, then it is very difficult for you to measure all these properties, microscopic properties. So always you should consider the group of molecules. You have large number of molecules. So in case of large number of molecules, velocity at every moment for gas molecule is zero, because we can assume that if some molecules are moving in one direction, so there is a equal probability that some molecules are moving in the opposite direction, and have the component opposite to the some set of gas molecules. So definitely the velocity is zero. That's why we are using here what speed, right? So it is very difficult for us to measure the velocity. So how, because this is a vector quantity, so how to make it a scalar quantity? So one very important, mathematical manipulation is there. If you do the square of this term, then you will get what? Scalar quantity, then you get what? Scalar quantity. So on this, I mean, squaring this term, we will get speed, and you know that we can write here, and scalar quantity u square is equal to u vx square plus vy square plus vz square. So this is equation 1. We can write this, right? Now see, I am considering a rectangular vessel, and see, this is the wall, vessel wall. This is also another, these two opposite walls I have shown here. The length is between these two wall is L, and this is the situation of this gas molecule before collision. This is a gas molecule. This is the velocity and vector, and these are the component, Vx component, Y component. I have shown here only two components, and I am considering here that this will collide, this molecule will collide along x-axis on the, wall of the container, right? So when it will collide with the along x-axis perpendicular collision, I am considering 90 degree. At 90 degree, this will collide. So after collision, this will bounce back, and see. So this is the components before collision: Vx component, Vy component. So momentum component I have shown here. Mass into velocity is the momentum. So these are the components, Y component, and this is the X component. Z component I have not shown here, and this is the momentum component of this gas molecule. After collision, there is no change in the Y component. There is no change in the Y component and Z component, but X component becomes, negative with respect to the wall, vessel wall. So if we try to find out what is the change in the momentum of this delta P of this molecule, delta P of this molecule. So delta P X, I am considering only X component here. So delta Px of molecule is equal to, we can write here, final momentum, final momentum minus initial momentum. So final momentum is m minus Vx minus mvx. So this you can write here, that minus 2mvx. So this is the change in the momentum of gas molecule. So what is the change of the momentum of the wall, right? So delta Px wall is equal to 2mvx, because you know the there is no loss in the energy, so momentum will be conserved. So if the molecule has this minus 2 mvx change in the momentum, so wall definitely 2 mvx plus, so the total momentum will be conserved, right? So this is equation. So now we have two equations. First equation regarding the velocity and speed, right? So see, this is square of this speed. Why we have done this square? To make this scalar, right? So this is the square of this speed. Word carefully you have to use speed, and these are the components, and this you can prove with the help of Pythagorean theorem, right? So, but not required. You can very easily understand how I have written this. And see, this is the momentum transfer or momentum change in the momentum. So final minus initial for molecule as well as for wall. And you know, collision is elastic, so total energy is conserved, momentum also conserved. Right now, come to the third point, time. See, I am considering here the total distance traveled by this gas molecule between two successive collisions. So after collision from here, this molecule may collide with the top, may collide with the bottom, may collide with the side walls. But I am not consider. I am not bothered about the other collisions, because I am considering only X component here. So it might be possible that this molecule may collide with the top of the container, with the side walls, but that will hardly matter, because X component will affect when will this will collide with this. So I am considering here two collisions with this wall. So our reference wall is this. Reference wall is this. So collision, suppose that molecule initially from here, this will collide from here. So this from here to here, this distance you should ignore. Count the distance from here after first collision from here, then this will collide here. After that, our reference wall is this. So between two successive collisions, so you have to start timing t is equal to 0 here after the collision, first collision with this. So in the between two successive collision with the same reference, not with other reference. So with the same reference between two successive collision, what is the distance traveled by the gas molecule? Obviously 2n. One is from here to here and other is from here to here. So this is very important point. Distance, the distance traveled by gas molecule between two successive collisions. Between two successive collisions is equal to 2L, right? 2L. Okay. It might be possible that this will collide with side walls, with upper and bottom walls, but that will not affect our X, this distance, X component distance. So Vx is unaffected. Vx will affect only when this will collide here and here, right? So this the collision is elastic, so there is no loss in the energy. So obviously only direction will change, right? So the distance traveled by between two successive collisions by a single gas molecule is equal to 2L. So you can write the time lapse between two successive collision, delta T is equal to 2L by Vx. So here I am taking only the x component of the velocity. So this is equation 3. See, one by one. First, we have make the formula for this velocity and square of velocity. So that is basically square of speed. Now it becomes scalar quantity. And second, I have made the formula for change in momentum. Now this is time. Now momentum transfer to the wall per second. Momentum transfer to the wall per second momentum transferred transferred to the wall per second, to the wall per second, right, is the momentum change per collision, right? So delta p x wall by delta t. So this is the momentum transfer to the wall per second. This is given by this equation. So this you can write 2 mvx divided by delta t is equal to 2l by vx. So you can write here mvx square by l. So this is equation 4. Hopefully all of you are getting this point. Momentum transferred to the wall per second is equal to this, right? So, and now second law, Newton's second law, you can write F is equal to m into a, m into a. So this is equal to, you can write m delta v by delta t. So this you can write here delta p by delta t. So this is equal to, you can write here this mvx square by l. So now you have calculated the force exerted by the gas molecules on the wall of the container, right? Now we can see we have large number. This is for a single gas molecule, so we have evaluated this. See, we have large number of molecules, n number of molecules here, and all molecules velocity x component, let it be x1, x2, x3, right? So the total force for n molecules we can write here F is equal to m vx1 square by l plus m vx2 square by l plus mx mvx square capital N, where N are the number of molecules, divided by L. This is equal to, if you take the sum of all these, then this is equal to capital N m vx square by L, right? So this is equation 6, where capital N is here total number of gas molecules, right? So this is the total force exerted by all the gas molecules. Okay, hopefully up to this everything is clear to all of you. And this time we should take the average here. See, v x is square and average of all the speed, because we cannot say that all gas molecules are traveling with the same speed. Some have some different components, vx component, vy component, vz component. So this is the average of all those molecules. So this Hopefully it is clear, right? Okay. Now we can write here Vx square average is equal to 1 by n 1 by n Vx1 square plus Vx2 square plus Vxn square, right? So this is right. So we can say Vx square, this is defined as the average of the square, the average of the square of x component of the velocity of x component of the velocity, right, of the n molecules, of the n molecules, of the n molecules, right? Now we have calculated total average force exerted by the gas molecules. Now we can calculate the pressure. P is equal to F by A, force per unit area. So force is equal to, we can write here N into M into Vx square average divided by A into L. Now this, in place of A into L, you can write here what, V, volume. So this is equal to N small m Vx square divided by V, right? So this is called what? Uh, Formula for pressure. This is called formula for pressure. So we can write here PV, or we can write PV is equal to capital N small m Vx square average. So this is equation 7, and this is the formula for pressure. But there is one problem. Here this formula is only in terms of x component of the velocity, right? So the gas molecules have no preferred direction of motion. So we can say that Vx square is equal to Vy square and Vz square, and should be equal to each other. So we can write here Vx square is equal to Vy square is equal to Vz square. So no preferred direction for gas molecule. So we are assuming that this is equal. So we can write here the U bar square is equal to, we can write 3 Vx square. Three Vx square. So by considering this, this, what? This. And from equation 1. And from equation 1, we can write this. Right? We can write this. So we can write here Vx square average is equal to 1 by 3 u bar square. Right? This is very important relation. Right? So we can write by considering this that all components are equal, and this is called equipartition of law of equipartition of energy. We are not considering here that x components have more value than y than z component. So we can write this. So your this equation 7 now becomes like this: PV is equal to 1 by 3 small m capital N now u square bar. So this is equation 8, and this is very fundamental equation. By using this equation, you can calculate the pressure of a gas in terms of the microscopic properties. Where what is this small m here? Small m is the mass of single gas molecule. Mass of single gas molecule. Capital N, I have already defined the total number of gas molecules. And what is this U bar square? So now you can define U bar square is the mean square speed. Don't write velocity this. Mean square speed. Mean square speed. Right? So this is the formula for pressure. So everybody should note down this formula, and this is very important formula. By using this formula, you can prove Boyle's law, you can prove Charles' law, you can define energy, everything you can define what you have defined with the help of equation of state at relatively low pressure. So this formula is also applicable at relatively low pressure. This is not applicable at high pressure, means at high density, right? So hopefully all of you are clear with this formula, and this is called kinetic gas equation. This is called kinetic gas equation, right? Equation 8 is known as kinetic gas equation. Kinetic gas equation, right? This is called kinetic gas equation. So by using this, you can calculate the pressure of gas molecules, or pressure exerted by the gas molecules, right? Good. Well, see, first I am taking this calculation of average kinetic energy of gas molecules. Basically, it is a translational kinetic energy. See, kinetic energy is of different types: rotational, vibrational, translational. So here I am focusing only translational by using this equation. See, we have two fundamental equations. PV is equal to 1 by 3 small m, capital N, U square bar, and PV is equal to nRT. By using these two equations, we can find out the relation for kinetic energy. See, left hand side is equal, so this you can write 1 by 3 m capital N U square average. This is equal to n RT. See, this is the number of moles and this is the number of molecules. So if you divide this equation by number of moles, so N by Na, so you can write here Na is equal to capital N by small n. This relation, the chapter 1, all of you are knowing this relation. So you can write here 1 by 3 small m into Na, right? U bar square is equal to RT. So if you see this equation, small m is the mass of single gas molecule, Na Avogadro's constant, so these two terms are constant. So if you see this is, mean square speed, see mean square speed, this will depend, R is also constant, depends on temperature basically, right? And for different gas molecules, for given gas molecule, it depends on temperature, and for different gas molecules, it depends on M also, right? Okay, now you can write, this is important relation. Now you can write the kinetic energy per mole average kinetic energy translational per mole is equal to 1 by 2 m U bar square, right? So we can write here 3 by 2 into 1 by 3 mu bar square, right? For 1 mole, this is for 1 molecule, so per mole into Avogadro's number. So here Avogadro's number also will come. So here also Avogadro's number will come, right? Per mole, Avogadro's number, right? 1 by 3 this. So this is equal to 1 by 3 mu bar square Na. This is equal to RT. So you can write here 3 by 2 RT per mole, right? So translational kinetic energy translational, not all. Translational kinetic energy is equal to 3 by 2 RT for gas molecules. And for n moles, this is equal to 3 by 2 into nRT for n mole of gas. and mole of gas, right? So in this way you can calculate the translational kinetic energy of gas molecules. Only translational, not vibrational, not rotational, right? So average translational kinetic energy per mole is given by this equation, right? So from this equation you can say that this translational kinetic energy or kinetic energy of gas molecules depends only on temperature molecules depends on number one depends only on temperature. It is independent of what mass, molar mass, or density, right? So mass of the molecules or their density, and and independent of mass of gas or density. So kinetic energy, translational kinetic energy, it depends only on temperature, and other energies, I mean rotational, vibrational, they also depends on some other factor. I am not talking here about rotational and vibrational energy. I am talking here only about translational kinetic energy. I will discuss rotational vibrational in the next chapter in thermodynamics, right? So kinetic energy, translation kinetic energy, this depends only on temperature. So if you have carbon dioxide and helium, both are the same temperature, although both have different number of atoms, both have different molar mass, both have different mass, but at the same temperature, both have same kinetic energy. This is very important generalization of this kinetic theory of gases, and this is very important as well, that kinetic energy is independent of the mass of the gas molecule, mass of gas molecule, right? Gas molecules or its density. Generally, in physics, all of you have this kinetic energy depends on the mass and velocity, like that. But for gases, see, it is independent of what? I mean, mass or density of the gas molecules, right? Now we can see here some in other way of this equation, right? Some other way of this equation, equation 8, PV is equal to 1 by 3 mn into u bar square. This is the equation, okay? So in other way, or we can write here 1 by 3 mn u bar square is equal to RT, right? This we can write, because PV is equal to RT, equation of state we can use. Now here, when N is equal to Na, suppose that this N is equal to Na, I am taking Avogadro's number of molecules, then then what we can write here is small m into Na, this is equal to capital M. And what is this capital M? Capital M is the molar mass of the gas. Molar mass of the gas. Yes, we can write this. When n is equal to, suppose that we have taken number of molecules is equal to the Avogadro's number, and small m is the mass of single gas molecule. So what is the definition of molar mass? Molar mass is the mass of Avogadro's number of molecules. So in this place we can write 1 by 3 capital M U bar square is equal to RT. Right? So this is also a very important generalization. From here also you can write U bar square is equal to 3 RT by M, or you can write here, if you take a root of this, so U square bar, this is equal to VRMS, this is equal to under root 3 RT by M. So VRMS is equal to the root mean square speed, right? So this is equal to root of root mean square speed. So this is one of the important molecular speed. This is called molecular speed. Root mean square speed is molecular speed, right? So root mean square speed, this also depends on temperature and molar mass of the gas, right? So you can write that URMS is directly proportional to square root of T and inversely proportional to of the molar mass. Means the RMS speed will increase as you increase the temperature, and it will decrease as you increase the molar mass, right? But kinetic energy, it depends only on temperature. See, kinetic energy, translational kinetic energy, it depends only on temperature, right? So if you see here that this U bar square, this will include that difference due to the mass. So that's why this kinetic energy becomes independent of the mass here, right? So root mean square speed or mean square speed, this will depends on the molar mass or mass of the gas, but kinetic energy, it becomes independent of molar mass or density of the gas molecule, right? Clear to everybody? Good. So this is called RMS speed. Now we have three different types of speed for gases, and all these speed means simultaneously exist for gaseous system. So suppose that we can now we can see the molecular speed, right? molecular speed of gas molecules of gases, right? Molecular speed. So we have three types of different speeds for gases. Molecular speed of gases. See, one is URMS, root mean square speed. This is equal to under root 3 RT by M, right? Another is U average speed. This is 8 RT by pi M, under root 8 RT by pi M. M is the molar mass, M is the molar mass. And one more speed we have, most probable speed. So most probable speed is equal to 2 RT by M, under root 2 RT by M. But whenever all of you are using this, so if you compare all these speeds, so you will find that the most probable speed ratio, average speed ratio, RMS speed, this will 1 ratio 1.128 ratio 1.225, means you can say you RMS maximum, then you average, and then you most probable. So we can say that at a given temperature in a gaseous system, all molecules do not have a same speed, means some of molecules or fraction of molecules have very large speed, fraction of molecules have very less speed, and maximum number of molecules have the average speed. So for many times, in many calculations, we always prefer average speed, not RMS, not most probable. But for calculation purpose, anyone can be asked to you for the numerical calculation. So all of you should remember this, and all these per mole, all these calculations for the per mole. And one very important point, all of you should be careful here, that M should be taken in kilograms per mole, unit of molar mass, kilograms per mole, right? Unit of molar mass, right? So unit of molar mass should be in kilograms per mole, right? So we have three different types of speed, and now you can see here that this variation of all these three speeds in the graph, if you see, this is the fraction of molecules, number of molecules, or you can say fraction of molecules, and here speed. So if you see here, you will find that, see, some of molecules have very less speed, some of molecules have very high speed, and maximum number of molecules you have here having the average speed. So see, these three are shown here, Most probable speed is this, after that average speed, and after that RMS. And as we increase the temperature, this more energetic, more speed of gas molecules what increases. So this you can show this on the graph at given temperature. This is for nitrogen. I think it is for nitrogen gas molecules at 0 degree Celsius C, and 1000 degrees Celsius, this peak will shift from here to here, and this becomes broadened, means more and more molecules now have more speed. More speed means more energy, right? So with rising temperature, speed increases, as well as what energy also increases. So at a given temperature, all gas molecules do not have same speed or same energy, right? Because at a given temperature the average energy is okay, but if you consider the individual molecules, then it is not that every molecule has same energy. That's why here the word I have used average kinetic translational kinetic energy, not the energy of each individual molecule, right? So here we are observing the properties of gas in a microscopic level in an average. Not we are not here pinpointing any particular gas molecule, right? And it is for us it is very difficult, right? So we have three different types of speed, which by using different experiment we have calculated this, right? And see, average speed, all of you are knowing, root mean square speed, that also all of you are knowing. What is this most probable speed? So if there is a, time to define most probable speed, so most probable speed, by this graph you can define most probable speed. It is defined as the speed expressed by speed expressed by maximum number of molecules, right? Speed expressed by maximum number of molecules. Suppose that if we have a container and we have certain molecules, suppose that we have n1 molecule here in this, suppose that n1 molecules with the u1 speed, n2 molecule are with u2 speed, and n3 molecule with u3 speed, right? And so and n2 are greater than n1 and n3. Suppose that this condition is given. N1 molecules are moving with u1 speed, average speed. N2 molecules are moving with the average speed u2. N3 is u3. And it is given then N2 is more than maximum. N2 are more than N1 and N3. So what is the most probable speed? So most probable speed is equal to u2. No need to calculate, right? How to calculate average speed? So average is equal to n1 u1 plus n2 u2 plus n3 u3 divided by N1 plus N2 plus N3. So suppose that temperature is not given, molecular mass is not given, this type of data is given, then you also calculate the average speed by using this formula, right? And this average speed will come equal to 8 RT by pi m, and this most probable speed, if you calculate, then it will come to the 2 RT by m, right? And similarly URMS also you can calculate here. URMS is equal to N1 U1 square plus N2 U2 square plus N3 U3 square whole divided by N1 plus N2 plus N3 power 1 by 2. So by using this equation you can calculate, right, RMS speed as well. So now you have both the methods. If this type of data is given, then you can calculate average speed, RMS speed, by using this formula. And if temperature is given and molar mass of gas is given, then you can, name of the gas is given and temperature is given, then you can calculate this by using this formula, right? So these are the different molecular speeds and their calculation. But remember, in most of the future calculations, we always prefer to use average speed because average is more, you can say, general term, right?